Before we get into a discussion of statistical inference for the difference in population variances, we need to talk about a distribution that is used for such problems, the F-distribution. If random variable x1 with degrees of freedom df1 and random variable x2 with degrees of freedom df2 both follow chi-square distributions, then the ratio x1 over df1 divided by x2 over df2 follows an F-distribution. That may not make a whole lot of sense yet, but it has implications for us in how we calculate confidence intervals and perform hypothesis testing for the difference in variances of two populations. A couple units ago, when we were talking about drawing inferences about the variance of a single population, we saw a quantity that followed a chi-square distribution. It was n-1 times s squared divided by sigma squared, and it had degrees of freedom n-1. So let's apply what we know about the F-distribution. x1 with degrees of freedom df1 follows a chi-square distribution. Let's say that x1 is n1 minus 1 times s1 squared divided by sigma 1 squared. And let's say that x2 is n2 minus 1 times s2 squared divided by sigma 2 squared. Both x1 and x2 follow a chi-square distribution. So we know that x1 over degrees of freedom n1 minus 1 divided by x2 over degrees of freedom n2 minus 1 follows an F-distribution. The n1 minus 1 quantities cancel out, and the n2 minus 1 quantities cancel out. So we're left with s1 squared over sigma 1 squared divided by s2 squared over sigma 2 squared. And this ratio follows an F-distribution. You can imagine that the subscript 1 could refer to the sample variance and population variance from population 1. And subscript 2 could refer to population 2. In this way, we can perform statistical inference about the variances of two populations. Broadly, the F-distribution has the same kind of shape as the chi-square distribution. It's truncated at 0 on the left-hand side, and it extends indefinitely in the positive direction. However, the F-distribution has two parameters instead of one in the chi-square distribution. The two parameters of the F-distribution are 2 degrees of freedom, df1 and df2. That's the degrees of freedom in the numerator, the degrees of freedom associated with population 1, and the degrees of freedom in the denominator, the degrees of freedom associated with population 2. So we say that the ratio of sample variances to population variances of population 1 and population 2 follows an F-distribution with degrees of freedom n1 minus 1 and n2 minus 1. To find a value on the F-axis, we can go to a lookup table. Since we have two parameters, we have more information to cram into one table. We have to use a different table for each upper tail area. As such, only some standard amounts of upper tail area are provided. In this class, we provide tables with 0.1 in the upper tail, 0.05, 0.025, and 0.01. Choose the value of the upper tail area you're interested in. Then you read the table as the value on the axis that corresponds to an amount of degrees of freedom in the numerator in each column, and then an amount of degrees of freedom in the denominator in each row. And again, space is limited, so we only have a handful of options for each degrees of freedom. Let's say we want to find a value on the F-distribution axis that corresponds to 0.05 in the upper tail, when n1 minus 1 in the numerator is 8, and n2 minus 1 in the denominator is 15. So we go to the 0.05 table, go over to the 8 column, and down to the 15th row, and that intersection is 2.64. Beyond 2.64 lies area 0.05 for an F-distribution with 8 degrees of freedom in the numerator and 15 degrees of freedom in the denominator. Also, much like the chi-square distribution, we don't have the ease of use of a symmetric distribution like z or t. We can't go to a lookup table, find a value on the axis associated with the upper tail, and then take the negative of it to find the lower tail value. But luckily for us, with the F-distribution, we have a relationship between the upper tail and lower tail areas. If we want, say, alpha over 2 in the upper tail, that's easy enough to look up, assuming that alpha over 2 is one of the standard values that we have a table for, 0.1, 0.05, 0.025, or 0.01. To find alpha over 2 in the lower tail, that corresponds to 1 minus alpha over 2 in the upper tail. So we want f sub n1 minus 1, n2 minus 1, 1 minus alpha over 2. This isn't given to us in the table, but we can calculate it as the inverse of f for alpha over 2 in the upper tail, with the degrees of freedom reversed. Going back to our lookup example from earlier, say we want to look up 0.05 in the lower tail, when n1 minus 1 in the numerator is 8, and n2 minus 1 in the denominator is 15. If we want 0.05 in the lower tail, that's the same as finding a value on the axis associated with 0.95 in the upper tail. To find it, we take the inverse of the upper tail f-axis value when the degrees of freedom are reversed. That is, f sub 815.95 is 1 divided by f sub 15, 8.05. In the 0.05 table, we go over to the column with 15 degrees of freedom in the numerator and to the row with 8 degrees of freedom in the denominator. This value is 3.22. The inverse, 1 divided by 3.22, is 0.311. So if we have an F distribution whose degrees of freedom, numerator and denominator, are 8 and 15 respectively, then the value on the axis associated with 0.05 in the lower tail is 0.311. So that's the F distribution. It's important for comparing the variances of two populations, and as a result, it's used in a statistical analysis technique called the analysis of variance, or ANOVA. We'll do a few examples and apply this distribution in some statistical inference settings.